Thank you very much. I'm hugely honored to be asked to give the Israel Physics Colloquium, and fairly terrified now that I've seen some of the people in the audience. But really, I'm delighted to be here. So I'll sort of trace what we've been doing in this thing called active matter from a little bit from early years, partly to set the stage, partly because many of the issues raised then have driven the field even now and are being resolved now. So that's where I am. These are my support from the Science and Engineering Research Board India and from a grant from the chair from the Tata Trust, which ran out now, I think. Anyway, so I'll tell you a bit of sort of early kind of prehistory, then some surprises in active fluids, an active defect unbinding phase transition, a funny kind of interaction that is inevitable in active matter, and then I'll summarize. Okay, first motivation. I mean, why do we study this class of systems that we call active matter, which I'll describe in slightly more detail presently? Major reason is, our hope is to formulate general laws governing the macroscopic properties, basically like doing condensed matter and statistical physics for collections of particles that are self-driven. It's that we can understand living matter as a kind of physical material. And it's hopefully, if we understand it well, we can also imitate some of the amazing things that it does. These are all stated in this way. It sounds very ambitious, but I think it's not a completely stupid enterprise to start to do this, to see, as we have seen in ordinary condensed matter physics, how many things we can say without a very fine, detailed knowledge of the systems we're looking at, only with a big picture, symmetry, conservation laws, and so forth. Okay. So that's the idea. And let me now be more precise. What do I mean by active matter? I mean particles that are alive, either in a genuine sense or in the narrow technical sense that, excuse me, narrow technical sense that these are systems made of components which are constantly supplied free energy, and they have some kind of internal machinery that converts that to some kind of movement. Regardless of the precise form of that movement, the point is these are systems made of particles or effective particles, effective component degrees of freedom, at whose level detailed balance is sustainably broken. Collections of such particles are called active matter. And you can actually understand on more or less pure thought grounds how to write down the equations of motion for active matter by taking a set of equations for a system at equilibrium, taking some subset, 1 degree of freedom, let us say, and instead of letting that be at equilibrium, maintaining a constant force on that degree of freedom, and then you will generate the generic equations of motion of active matter for the other degrees of freedom. I will not go through this, as this is a colloquium talk. I don't want to give you a very nerdy and detailed presentation of building equations of motion in that sense, although there will be equations in the talk. But there are papers by us that talk about this in Journal of Statistical Mechanics, which you might like to look at. Okay, so what do we want to do? We want to take something like this, this flock of millipedes, and say, it's a walking liquid crystal. And can we build the equations of motion for this object? This is a movie which I forgot to credit. It's my friend Sriram at University of Hyderabad who took this. And as you can see, some kind of spontaneous ordering seems to have taken place here. But more generally, you can have active matter in a wide variety of types. You can have liquid crystalline structures like the spindle within a living cell. You can take filaments and motors out of the cell and make active liquid crystals in a Petri dish. You can have bird flocks flying over the building that my student took movies of, that I would love to make a theory of, but I don't have. And I don't know how to switch this off either. Okay, I did the wrong thing. I switched off my talk. Just a moment. I'll bring back my... Oh, is my talk still there?
Yes, it is visible.
Yeah, okay. You can also have artificial active matter. You have a surface which is vibrating, and you have a particle which actually moves around purely by virtue of the fact that its shape allows it to transduce that vibrational energy into translational motion in the plane. And you can have catalytic particles in a fluid containing a compound that the catalyst breaks down. And so these things start with, so you can make artificial swimmers. You can even argue that if you take some two-dimensional material and you pump it in the third direction, the sustained flux of energy, let us say by connecting its two faces to leads maintained under thermodynamically different conditions, the effective two-dimensional dynamics of that system is a kind of active matter dynamics. Now, I won't talk about things like quantum active matter, but it's worth keeping in mind that one could do such a thing. Apart from the generic driving conditions, you can ask about the kinds of particles and the kinds of order you can have. And you can have particles that are vectorial, tensorial, or scalar, or more complicated. And you can have macroscopic states of order, which are vectorial, like this collection of particles that is not only pointing in some direction, but actually going somewhere. You can imagine particles that point in some direction, but which are aligned only with respect to their axes and not their heads and tails, in which case you'll get something whose macroscopic symmetry is that of a nematic. Or you can have particles which are themselves head-tail symmetric but elongated and form this a nematic crystal of this sort. You can also have particles which don't have any particular shape anisotropy, but because of some chemistry taking place, their surface start running around, and you can make a kind of scalar active matter with typical phenomena that you'd get in systems characterized only by a density field rather than orientation field, like phase separation or microphase separation and so forth. Okay, and apart from the types of particles that have order, you have different dynamical regimes. Now, in systems at thermal equilibrium, you know that if you've got a collection of particles with a given pair interaction, then the phase diagram depends on the pair interaction, and you should, at thermal equilibrium, get the same phase diagram whether the system is in a momentum conserving situation or in, let us say, a situation where the momentum has a sink. But for out of equilibrium systems, no such guarantee is available when you change dynamical ensembles. So it makes sense to consider wet and dry active matter separately. So, fish schools and collections of those motile particles on the surface will have different kinds of statistical mechanics. And we'll say a little bit about both of those during the talk. As I said, I'll say a little bit about prehistory. 51 years ago at this point, two eminent fluid mechanicians wrote a paper containing the word active stress in the title. So we thought we were the first to invent the word active stress. It turns out Finlayson and Sriram said it in 1969, and they meant the same kind of thing as us. They talked, and these are direct quotes from the paper, they talked about motion without the intervention of outside forces. They said that such engines operate in living systems. They commended this general area of research to everybody who likes complex fluids and liquid crystals and polymers and colloids. They said there should be these systems need for a microscopic theory of statistical mechanics not yet detectable on the horizon. Oddly enough, they weren't interested in the kind of active matter physics that has dominated the field in the present day, which has to do with uniaxial, contractile, or extensile forces exerted by motors or other such processes acting on biopolymers. They kind of dismissed it. They said you should think about other stuff. Nevertheless, the main point is these guys said all this. They wrote a beautiful paper. They talked about some oscillatory phenomena in some kind of cellular aggregates, but it absolutely didn't launch the field. And I think the reason it didn't launch the field is that the theoretical framework for understanding order, fluctuations, broken symmetry, and all that as a generic class of phenomena for which you can write theories wasn't available even for equilibrium systems. You didn't have Mann, Mazenko, ferromagnets paper. You didn't have Hornberg and Halperin's classic review article. So theories of sort of fluctuating hydrodynamics, broken symmetry dynamics were not really available. So I comment a little bit on this in a kind of lightweight article I wrote sometime last year for George Gabriel Stokes's 200th birthday. I should probably keep my phone out so I can tell the time. Okay, so anyway, so active matter didn't get launched in 1969. So what happened? So let me now, this is still kind of history, but I want to set the stage with some key results. We checked, and actually a computer scientist who made animation movies for Hollywood, invented flocking models in which particles try to stay out of each other's way, don't try to go too far from each other, and try to align with each other. And what they found in these systems was that if the densities were high enough and the noise levels were low enough, you'd get ordered states spontaneously. So you're breaking spatial rotation invariance. And as a result, of course, it was a non-equilibrium system, you got moving states. You can see this kind of phenomenon in real systems also, like this experiment by Chabot et al. On keratocytes, in which you also see flocking if I move this. So by the way, is this this thing in which I can see Sneer and myself, is that coming in the way of the viewing?
No, that's fine.
All right.
The slides are
the rest of the audience doesn't see it. Great. Okay.
So
anyway, so there are these things called, so Tonoran 2 showed not only that you get a flocking transition, but that subject to some conditions, you can actually get long-range flocking order. Remember, this is breaking O2 symmetry, long-range flocking order in 2 dimensions in these systems, which of course is happening. It's not a violation of the Mermin-Wagner-Hohenberg theorem. It's an evasion of it because the systems are out of equilibrium. So our interest really was piqued by merely the existence of flocks, but the fact that flocking very often takes place in a fluid medium. And all these theories up to that point were about flocks on a kind of dry terrain, on an abstract passive momentum sink. So we got interested in this, and we discovered that flocks in fluid are really different, and because momentum conservation really makes a huge difference. So we wrote down by kind of pure thought the equations of hydrodynamics for systems characterized either by a traceless symmetric tensor or by a polar vector. We wrote down an equation for the orientation, an equation for the hydrodynamic velocity field. The equations were basically a transcription of the well-known hydrodynamics of liquid crystals with one augmentation in the momentum equation, namely a stress directly proportional to the local orientation. Okay, and if you had a concentration field, in addition, a particle current directly proportional to the divergence of that orientation tensor. So this changed everything, and quite dramatic things happened. For example, we were able to show that if you had a collection of particles swimming around, then depending on whether they swam by pushing fluid out along their body axes or pulling it in along their body axes, the mere presence of swimmers could decrease or increase the viscosity of the medium, not because of entanglement, not because we're secreting some goop, but simply because of the flows they set out in response to an imposed flow. Not only that, if you tried to produce an aligned state of these systems, then the guys that swam by pulling would inevitably go unstable in splay, and those that swam by pushing would inevitably go unstable in bend. And within a Stokesian hydrodynamic theory, these instabilities in an unbounded system were without threshold. So basically, you can't have aligned Stokesian, you can't have Stokesian active liquid crystals, period. So this we showed a long time ago, and it kicked off a flurry of activity which has been going on till now. The cleanest confirmation of these predictions was really by the group of Francesc Sagués, who showed who took a microtubule motor ATP liquid crystal, set up in a splayed geometry, and let it go. And these are pusher liquid crystals, they should go unstable and bend, and rather spectacularly they do so. And they eventually dissolve into a defect-ridden turbulence. So the linear instability of the aligned state of active pneumatics leads to defect proliferation and leads to a kind of defect turbulence, similar to the kinds of things that people have discussed in contexts like complex Ginsburg-Landau and so forth, but with some important differences. You see similar phenomenon and similar conformations in many settings, one of my favorites is this spontaneously rotating nucleus inside a cell, which is rotating because the motors and filaments around have created a spontaneous flow because of this instability. Anyway, so that was one background remark in wet active matter. I'll come to the new results presently. Another background remark in from that era, from 2003, was that even if you have a flock that isn't in fluid, and even if the flock consists of particles which are head-tail symmetric, like the ones I just discussed, a headless flock, even without fluid, is totally different from a dead flock. And the reason, A, is that it turns out curvature gives rise to mass flux, which gives rise to giant density fluctuations, which I will not discuss. And curvature, because it's very large in the vicinity of topological defects, gives rise to the motion of topological defects of strength half. I'll come to that. So this observation that strength half topological defects are spontaneously motile was first seen by Vijay Narayan, Narayan Menon, and myself in experiments in 2007. We predicted it and we saw it in the experiments. It's not widely appreciated that actually those experiments and that qualitative prediction was the precursor of much later work on this subject. Right. So now that ends the prelude and history and background. Let me come to the first topic. I'll reverse the order. I'll tell you about dry, that is active matter on a substrate, and I'll consider a system in a state known as the nematic liquid crystal, which means a bunch of rod-like objects all on average macroscopically aligned and lying on a surface. And by whatever means you like, these particles are being energized in such a way that they're held out of thermal equilibrium. The actual experimental way in which it's done is they're placed on a surface, and the surface is vibrated along up and down, and these particles move more along their length than transverse to their length. So we argued earlier that these plus half defects, which I'll say a little bit about, act like particles. What happens is the following. When you have a nematic liquid crystal, you have topological defects of two kinds: half integer strength and integer strength. The ones with half integer strength are the most abundant. What happens is the orientation goes through plus pi or minus pi as you go around the core of one of them. They are widely seen not only in equilibrium liquid crystals, but also in liquid crystals made of living and actively metabolizing elongated cells, as in this work from Masaki Sano's group. And given that they're motile, so as we remarked back then, the curvature on the plus half defect should make it move in the direction of its nose. Given that they're motile, this poses a rather awkward question. You presumably know from Berezinski-Koslitz-Thouless physics, XY model physics, that in thermal equilibrium, defects of this type attract each other with a logarithmic potential, and therefore the balance between energy and entropy is such that they'll unbind above a certain temperature larger than the scale stiffness, and you get a melting transition. If these plus half defects are motile, it means it's as though when you have a plus half and a minus half, the minus half is trying to attract the plus half, but the plus half is setting off on its own because it's motile. It's as though there was a negative linear potential fighting with the logarithmic attraction. If that's the case, the effective potential felt by the plus half has a logarithmic attraction, but a minus r, and therefore plus half and minus half should be always unbound. There should be no active nematics. However, experimentally, as well as in particle-based simulations, an active nematic phase does exist. So what's going on? So what's going on can be understood by writing down a theory of the positions of the plus half and minus half defects. The plus half and minus half attract each other with a force field, which is the gradient of the logarithmic potential, but the plus half has, in addition, a self-propelling velocity. So if you build a theory of this sort and you include noise, then what you realize is that this picture is a little naive, it makes sense only if the plus half keeps moving without changing direction up to the effective top, the position of the effective top of that barrier. If it undergoes rotation diffusion such that it loses its way, this picture is internally inconsistent. And so what really happens is that if the plus half moves persistently without changing its direction, it will indeed unbind. If, on the other hand, noise is so large that the plus half and minus half are pulled apart for usual thermal equilibrium reasons, they will unbind then also. So the correct physical picture is that if you plot activity here and a kind of noise temperature here, for any given level of activity, if your rotational diffusion is low enough, you will always be melted. If your rotational diffusion is high enough, you'll always be melted. This is an active melting. This is merely a shift of the traditional BKT phase transition by activity. And so what you should get generically is a nematic phase in between, melting at low noise and melting at high noise. So this is what we predicted a couple of years ago. There haven't been any clean tests of this in experiment yet. But so that's one story of relatively new physics. This is work done by Suraj Shankar, Sriram Mark Boyd, and myself a couple of years ago. Okay, now let me go back to wet active matter. I told you that if you have a bulk fluid, then in the Stokesian limit, it's always unstable. What about if I take the same system and now think of a thin film of fluid? So what you're looking at is a top view. Imagine a thin film of fluid on a surface with a lid on top. So all that long wavelength hydrodynamics that destroyed the ordered state should be severely altered by this confinement. So does that suppression of the long wavelength hydrodynamics simply give you something which is effectively like a system in which you have an orientation field and you can forget the velocity field, you can forget the hydrodynamic flow? The answer is no. It's a little tricky to figure out, to explain in detail exactly why, but basically, when you confine an active suspension between two plates, you still have a residual constraint, namely, even though the velocity field is heavily damped by the walls, the velocity field is still constrained by incompressibility. The presence of this incompressibility constraint alters the dynamics in such a way that if you have an aligned state and theta is the number Goldstone mode, the transverse fluctuations of the aligned state, it ends up having a relaxation rate because of the incompressibility constraint that doesn't go to zero at zero number. If you add a noise here, and the noise is an ordinary non-conserving noise, you will get Angate fluctuations that are finite. So the sort of the ghost of the hydrodynamic interaction in the presence of confinement so radically alters the long wavelength dynamics that depending on material parameters, you have a system that's either always unstable or always stable. If this thing has the correct sign, it's positive, it's always stable, and that means orientation fluctuations have, in some sense, in a field theory sense, a mass. So even though it's a number Goldstone mode, like in the Higgs mechanism, from a field that has long-range effects, it acquires a mass. And so a confined, active, wet polar flock has extremely strong long-range order, not relying on any mechanism coming from the normalization of stiffnesses, from nonlinearities, but from the residue of the hydrodynamic interaction. So this is something we showed, which came out this year by Ananya Maitro, Pragya Srivastava, Krishna Marchetti, Martha Lenz, and myself. The story for a nematic state under similar confinement is also very interesting, but I will not, I won't go into it. That came out a couple of years ago with the same authors and one more, if I remember right. And I'll commend you to that article. So there are surprises in confined wet active nematics as well. Okay, now continuing with wet active matter, let me talk about active fluids. Let me remind you how active fluids, as I said, the argument I gave you earlier is that active fluids without inertia are unstable without threshold. What my student Ryan Chatterjee, the late Aditi Sinha, another student Navdeep, and my colleague Prasad Perlekar did was to take up this problem and ask, well, you know, clearly large-scale flocks where inertia is important do exist. You have big fish schools. Can we start to bridge the gap between completely inertia-less Stokesian suspensions and active fluids on scales where inertia is important? The important thing to note is that the instability of active fluids without inertia is actually a funny matter. It's governed by a single time scale, which is wave number independent. The active stress, which I've called W here, has units of stress. The stress divided by viscosity has units of inverse time. So instabilities in a Stokesian aligned active suspension grow at a rate which is essentially independent of wave number, as long as you're at length scales big compared to the scale at which elasticity can help you. What happens when you include inertia? Well, I do want to occasionally put up equations of motion. If you include inertia and you write the equations of motion for a vector orientation field and a hydrodynamic velocity field, you can think of U as the suspension velocity field. You can think of P as the orientation of your particles that are flocking. That orientation can be advectored by the hydrodynamic velocity field or by itself, because this orientation is also a velocity. It can be aligned by coupling to flow. The symmetric part of the velocity gradient aligns it. It can be rotated, or it can relax due to an energy function that promotes local moment formation and has elasticity. So what do these equations tell us? The difference between these equations and the equations we use to draw the conclusion that flocks in fluid are always unstable is this. We won't, it turns out, be working in a regime where U dot grad mu is important, but unsteadiness at the very least will end up being important, and we'll see what happens, okay? And we'll consider only systems in which the active stresses are of the pusher kind, that is, of this kind, that push out along their axes and go unstable, therefore in bend. There are some important dimensionless numbers in this problem. The most important is this ratio, which looks like the ratio of two stresses, a stress formed from what looks like the inertia of self-propulsion and the active stress scale. You can view this, okay, so and there are a couple of other parameters which I'll come to in a moment, which have to do with the ratio of the rate at which orientation diffuses to the rate at which velocity gradients diffuse. This number is likely to be very small because it is molecular of colloidal systems. This number is our important control parameter. You can also view it as a speed ratio, the square of a speed ratio, the self-propulsion speed, to a speed made from the active stress and the mass density of the system. Rho is the mass density, okay? So, so what happens? So I won't trouble you with the algebra. If you take these equations and perturb about a macroscopically aligned state, what you find is that the growth rate, which is the imaginary part of the eigenvalue, depends very, very strongly on this crucial parameter, the relative importance of inertia and active stress. Actually, maybe this is a moment at which I should pause. So are there any questions up to this point, or have I completely left you in the dust?
Okay, if someone wants to ask a question, you can just
Sure.
himself and
No questions?
okay, so let's continue. Maybe there is one. We have one. Yes.
So can I ask about, you said that the half defects are repelled or attracted. What happens to the integer number defects? Are they stationary?
Yeah, so we haven't looked very much at integer strength defects in the nematic case. Integer strength defects will come up in what I'm going to talk about now. Integer strength defects, the point is, supposing you take a system at thermal equilibrium. Integer strength defects then are more costly from the energy function than half strength defects. So the defect unbinding transition is completely dominated by half integer strength defects. That's essentially the reason we don't worry about them. So we haven't tried to make a theory of the proliferation of higher strength defects, essentially because if you like, we're perturbing off the equilibrium theory. In the equilibrium theory, the half strength defects have far lower energy. And so the unbinding is that of half strength defects. So that's why I didn't talk about it. In what I'm going to say about flux in fluid, integer strength defects will play an interesting role.
Okay, thanks.
Thanks. No other questions? Should I go on?
Maybe we can continue. We take questions.
Okay, all right. So what we do here is we take these equations of motion, and we ask basically, how does the presence of unsteadiness change this picture? See, the idea is this: when you perturb, let's take this case. If you perturb the oriented state, then if you look at the stresses carried by each of these particles, if you perturb like this, the pushing outward stresses will drive flow this way here and this way here. The onset of that flow within the strict Stokesian approximation is instantaneous. So you perturb, there's flow immediately, that flow rotates these guys in the direction in which your perturbation had already rotated them. Question now is, what happens if there's actually a lag, because it takes time for the velocity field to build up? Just that simple question changes the story, and this instability now is going to be mitigated a little bit by the fact that it takes time for the velocity to kick in. And what happens is that if the self-propulsion speed is too small compared to the scale of speed set by the stress, then if that means that parameter r is too large, then the instability goes completely away. The purple line says that if r is very large, you actually don't have the instability at all. An aligned state is linearly stable. If it's of intermediate, if on the other hand it's very small, if it's zero, then what you have is a growth rate that is non-vanishing even at zero wave number. If it's small but not zero, you see a trend that looks like the Stokesian trend, but which eventually turns over, and if you zoom on this bit, it's actually a growth rate that's linear in wave number at small wave number. A growth rate linear in wave number means that these lines act as though they have a negative tension. You perturb them, and you have a growing mode, but the growing mode grows at a rate linear in Q. Meanwhile, these guys are also moving. Remember, we're talking about a polar flock characterized by a vector order parameter. Things are moving along. So the point basically is, when you perturb like this instability is building in at a rate linear in Q. But on the other hand, these guys, which I've shown as headless and actually they have a head, they're moving along, and they'll escape a region of a given size in a time proportional to that size. So it turns out that if you've got a head and you're moving, you can actually outrun your instability. And this parameter tells you whether you can outrun the Stokesian instability or not. So what you find is that if you are fast moving enough, you can outrun the instability. If you're slow moving, you basically meet the same fate as your Stokesian siblings. In between, you can be in a situation where the instability is not as violent, the growth rate is only a quarter wave number square. So this is what the linear theory tells you. We haven't tried to do an analytical theory of the unstable state in each of these cases. Instead, we took the system and put it on the computer and studied it pseudospectrally, numerically. And what Ryan found, I hope this works. Go. Excuse me.
Sriram, did you pause or?
I think we got disconnected from
We got
Sriram.
disconnected. Okay, let's wait for a second. Yeah, hopefully Sriram will reconnect momentarily. Okay, you back? And
I seem to be back now.
yeah, okay, you got.
Yeah, I seem to be back now.
Let's try to share your slides again. And,
Okay, all right. Yeah, I think the movies were too much for the. So what happens basically? Let me do this in non-presentation mode for a minute. Can you see it?
yes, it is visible. Yeah.
Hello? Yeah. So when the growth rate is linear in wave number, you get a madly defect-ridden state. You get three-dimensional hedgehogs of strength plus and minus 1. And it's a defect turbulent state. If, on the other hand, you go to the case where the aligned state is weakly unstable, only at order wave number squared, you get a much milder state. You get fluctuations, you get noise, but the system goes back to being aligned. So the state that is order q squared unstable is statistically still an aligned state, rather amazingly. And what that means, if I can get this slide to advance, is that you have a transition from defect turbulence to phase turbulence, and the phase turbulence state has macroscopic order. It's just got noise, that's all. This, we don't have a detailed analytical theory for it all, obviously, but the numerics shows this. And it's rather like in the Kolmogorov-Sierpinski equation when you have a linearly unstable height profile, but which eventually becomes something with a positive diffusivity and noise. And numerically, if you measure the macroscopic vector order parameter, then as a function of my favorite parameter R, you go from a state with no order and lots of defects to a state with well-defined macroscopic order. The orientational correlation function becomes more and more long-ranged with a length. This is the inverse length plotted against 1 over my control parameter, and that inverse length decreases, that is, that correlation length increases as you approach the transition. So as a flocking transition driven by inertia, inertia suppresses active defect turbulence. That's what happens. Okay. So how much time do I have left? Do I have about 10 minutes?
Let's say about 10 minutes, yeah.
Yeah, okay. So that's all I'll say about wet flocks. Let me come to a completely different topic, non-reciprocal interactions. You know that, so that's it for flocks at the moment. You know that non-reciprocal interactions are ubiquitous and we all experience them in our lives. Someone is attracted to someone else, but that person is repelled by this person. So it can happen for social reasons. It can happen because, for instance, one locust is trying to eat the locust in front of it and the locust in front is trying to escape. So all over the place. Non-reciprocality, of course, is expected in systems that don't have an energy function because of the pair interaction between two particles is not governed by a pair potential. Then there's no reason why the force exerted by B on A is equal and opposite to the force exerted by A on B. This is explored in many ways, in particular by Surupriya Saha, Rami Golestanian, to some degree by our work in active colloids, by Cristina Marchetti and a student in a similar context, by Vincenzo Vitelli and others in non-reciprocal X-prime models. I will tell you two stories about non-reciprocal interactions, one about motile particles in an elastic medium and one about active cholesterics. I'll be fairly quick. We were worrying about non-reciprocal interactions actually back in the days when we also started to worry about active matter. So Jayjit Das and Madan Rao and I asked, if you have, imagine you have two spins, and imagine that the exchange coupling that exerts a torque on spin I due to spin j is different from the exchange coupling that exerts a torque on spin j due to spin I. And you can imagine these two things are pointing in slightly different directions. One of them may end up doing much more of the turning, the other much less of the turning to align. So we studied this in the context of Heisenberg magnets. That problem sank without a trace. I mean, that paper sank without a trace. But we came back to it when thinking about flocking models. And then more recently, we started looking at it in the context of motile particles in an elastic medium. Now, people have studied active particles in fluids a great deal. Sam Safran and group have studied active objects in an elastic medium, but ignoring their motion, but looking only at their force dipole character. Silke Henkes and company studied motile active Brownian particles in an elastic medium, but didn't look at their elastic interaction. I think that both motility and force dipoles should be important when active particles move through an elastic medium. So we started to look at that problem. And the idea basically is you've got motile particles moving through an elastic medium, and they distort the medium, and the medium distorts other particles as a result. So you can read about this. It's still on the archive. It's work done by my student Rahul Gupta, Harsh Soni, Roshan Kant, and his PhD advisor Ajay Sood. There's some experiment in this and some simulation and some theory. We got interested in this actually because we were interested first in active particles in a monolayer of beads. So this is a vertically vibrated monolayer which you're looking at from the top, and you've got rods moving along, and the medium is, although very dense, it's actually fluid, and the flow generated by each particle is aligning other particles and producing a flock without them touching each other. So we then, this is PhD work of Nitin Kumar with Ajay and me. We then decided to say what happens if the medium is so dense that it's actually crystalline. So again, it's a monolayer of beads. The experimental system, the rods are made of brass, the beads are made of aluminium. These pictures are from a simulation, but it's a mechanically, slavishly faithful simulation. And what happens when the bead medium is fluid is that as these particles move, they drag a few particles, which I've marked here, with them. When the medium is crystalline, these guys still succeed in moving, but they don't drag the medium with it. If you look at the flow around the particle, when you go to high concentrations, so the medium is crystalline, you just get tiny amounts of back and forth movement and no coherent flow. So what does happen? Well, to see what happens, you can write down a theory. The theory is of one active particle, which I already showed you, these guys. One active particle moving through a medium of beads. So let's say the particle has an orientation n, it has a position r, it moves with a speed v0 in the direction in which it's pointing. Its orientation forces the medium in the minimal simple way possible, namely it produces a local point force pointing in the direction of its nose and situated at the location of the particle. The location of the particle, however, is moving. Okay? U is the displacement field, not the velocity field, the displacement field of this elastic medium. Let's assume it's governed by some kind of Lamé elasticity. Let's ignore its inertia altogether. There's a friction. And then let's say the orientation is acted on by the medium in two ways. One is that the medium, that curvature in the crystal planes or crystal lines of the medium produce a vector with respect to which n can align. And strain of the medium produces an axis with which the rod-like object, whether it had a head or not, can line up. This is, of course, lower order in gradients, and it's all that I'll discuss today. So you have particle moves following its nose, it forces the medium, it sets up strains in the medium, not flows. It may melt the medium locally, but macroscopically it sets up strains. Those strains reorient other particles. And what happens? what happens is if you first just ask, okay, I've got one particle moving along, what's the strain field? Because it's a moving particle, that strain field is the strain field of a moving object and therefore comes with a wake, right? Because if I co-move with one single particle, this du over dt becomes v dot grad u, which if it's moving the x direction is v naught dxu. And so the displacement field produced by this this moving point force is a displacement field with a very funny character. You can solve it in terms of modified Bessel functions. The important thing is that if you look in front of the particle and behind the particle, the displacement fields are very different. It's strongly screened in front of the particle, and it decays only as 1 over the square root of distance behind the particle. So one moving particle leaves a strong wake behind it and gives very little warning of its approach in front of it. It's an overdamped elastic wake. And you can measure this. It's hard to measure this in the experiment proper, but we have a particle-based simulation, which is really an experiment, and you can extract those displacement fields, and they agree reasonably nicely. And then you can ask what happens if you put two particles, okay? So imagine putting one particle in a strain field produced by another particle. What you find is that if you make it align with the principal axis of the strain, then if you put two particles in there, they approach each other in the manner shown in this figure. And you can check this in experiments. This is the experimental setup in a Jesuit's lab. It's an industrial shaker, and there's several millimeter sized particles, half centimeter long. And they walk because when you bounce them up and down, because their two ends are different, when one end hits, it gets impelled along. The beads, which are also present, bounce up and down and essentially go nowhere except for a little bit of diffusion. And what you find is indeed that if you start out two particles like this, they attract each other, they turn their heads towards each other and find each other. You see it in the experiment, you see it in the simulation. If they're a little too far apart, noise makes them lose the way. So as a function of separation, if the separation is much more than few tens of particle dias, they go away. If the medium is fluid, the flow setup instead would make them repel. Okay, so they repel when the beads are fluid. Bead layer is in a fluid state, but they turn towards each other and attract through the mechanism we talked about when the bead layer is in a crystalline state. And what's cool about this is that if you now consider a situation where one particle is pointing this way and the other is pointing that way, and they're moving, then what happens is as this particle moves along, it really gives no warning of its approach to the particle in front, and it turns and catches the particle in front. So this, which you can see in the simulation and the experiment quite nicely. This is really interesting because it's a new generic way in which a particle could pursue another particle. Because the interaction isn't a pair potential, the interaction proceeds indirectly by a strain field produced by one particle rotating another particle, and the speed at which the particle moves being an intrinsic property of the particle rather than set by an attractive force, you get this non-reciprocal capture. It seems to me that this should come up somewhere in the living world. I don't know that it's been looked for in biological systems, but it's hard to imagine that particles moving through the extracellular matrix wouldn't use this. Okay, that's all I'm going to say about this. Can I spend 5 minutes on active cholesterics?
Okay.
Until you stop me, I keep talking.
I can't say no.
Okay. So, active cholesterics, a cholesteric liquid crystal is something in which the orientation has a one-dimensional static wave. There are no true layers. Any section is the same as any other section. Yet, macroscopically, the long wavelength elasticity and hydrodynamics of cholesterics and smectic liquid crystals, which are truly layered because of the density modulation, are identical. So hydrodynamically, in thermal equilibrium, cholesterics and smectics are the same thing. The chirality of cholesteric does not affect the long wavelength elastic and hydrodynamic properties. What happens in active systems? This is work with Swapnil Kole, my student, Anyo Maitro, and Gareth Alexander. We built active cholesteric hydrodynamics in a very generic way. So let's, rather than describe a cholesteric as a density wave or an orientation wave, we say there's some scalar and the system is chiral. So let's build a generic theory of a one-dimensionally modulated state of a scalar together with the presence of chirality. And let's build the hydrodynamics including the equation for the momentum density. That equation will have a stress. One contribution to that stress built on pure thought grounds in a system with chirality is this object. Here it is. It's 1 grad on 2 grads. I'm sorry, that's a typo. My bad. Oh God. Okay, it's a complete dog's breakfast. I won't even try to rewrite this object, but it's a simple, it's a minimal second rank tensor that can be built from 2 gradients on psi. Okay, it looks like it has 3 gradients and therefore should be unimportant to the long wavelength dynamics, but it turns out it isn't. It gives rise to a force. If U is the layer displacement field, so you've got these layers, their displacement is a displacement field. This term gives rise to a force which points tangent to contours of constant mean curvature. So this is del squared U is the mean curvature. Okay, so this where epsilon ij is the epsilon tensor dotted into the layer normal direction. This object is invariant under z going to minus z because if I reverse z and reverse epsilon and reverse u. So you have this interesting force. Something interesting also happens in 2 dimensions, but let me concentrate on 3. So on 3, what happens is the following. First, if you didn't have an active cholesteric, you just had an active symmetric, then the intrinsic uniaxial tension normal to the layers gives rise to an unrelational instability. If you fold in this weird chiral term, that gives you, if you have spontaneous undulations, the weird chiral term gives you circulating velocity fields, gives you a vortex lattice of the velocity field in this fashion. Now, you can do something else, which is you can suppress the undulation instability by uniaxial compression. If you do that, you can switch off this vortex lattice. So what you have in this system is a controllable vortex lattice, an on-off switch. Applied uniaxial compression is an on-off switch for a vortex lattice in active cholesterics. There are other similarly cool effects in 2-dimensional chiral stripe systems, which I will let you read about. This is almost written up. With some luck, it will be on the net in a few days. Okay. And so I'll stop here. I hope I've convinced you there is such a thing as condensed living matter physics. I've shown you that you can make stable flocks in fluid. I've shown you that inanimate particles can chase and capture each other. And I've shown you that cholesterics and symmetrics are not identical when they're active, and they have this fabulous self-stirring instability which you can turn on and off with your hands, more or less. More generally, I've shown you a framework for describing the mechanics of living, breathing matter. And it's a story that started a good many years ago, but shows no signs of ending. My talk, however, will end here. Thanks for your attention. I'll be happy to take questions.
Okay, so let's first, just virtually, thanks Sriram for an inspiring talk. So we have some time for a few questions. So let's start. Itzhak?
Yeah, Sriram, this is Itzhak.
Hi, Itzhak.
How are you?
Hi.
I have a question. I mean, you discussed here this kind of living matter, or actually, I'm not sure even living matter, but of matter, where it's really this kind of colloids which are propelled, right? But I mean, there is a lot of this other stuff, let's say what happens in biology, actually, mostly, it's that energy is being pumped into the systems on very small scales. And so this the whole issue of how exactly the energy is, entering the systems is rather tricky. And definitely it's not standard hydrodynamics really. So because you are not basically pushing energy from some large scales or from motion of large objects, but really from on a molecular scale. So I mean,
yes.
Yeah, and
So
so I
that is
was wondering, I
precisely
mean,
the spirit. So let me comment on that, if you don't
Yeah.
mind. The point is, what we mean by active matter is precisely systems in which, at an intrinsic sort of particle scale, energy is being fed in. So it basically amounts to saying you take what you know how to do in ordinary condensed matter physics,
exactly.
you suspend energy conservation, you keep the other conservation laws, and you introduce a sort of, you assume the system is suffused with an energy source. Now, obviously, this approach has its limitations because you need to take waste, whether it's waste heat or waste product, out of the system. But to a reasonable approximation in living matter and in quite nice experimental systems, you can actually produce states in which you have a homogeneous energy source everywhere, and that energy is being dissipated, and these things are happening. So it's exactly in the spirit that you describe it when this is being done. So it's not, it doesn't have to propel colloids. You can just say, I'll take a scalar phase separating system and ask what the active version of it is. I suspend time reversal invariance, I suspend conservation energy, I write down the equations of motion, I can make predictions. So it is actually in the same spirit as you're saying.
But there is, yeah, I understand. But I mean, there is a tricky point, I mean, because I was working on this. And so the tricky point is that somehow you can think about it as a kind of noise, of active noise that enters the system. Because really, I mean, there is, below this hydrodynamic level of description, there is always the more microscopic one, and you coarse grain over some small scales. However, here, I mean,
Yes.
the energy is supplied on these scales, which you normally coarse grain. So
exactly, but the point is, you don't see an energy source term in the equations of motion except in the form of terms that would not have been permitted in the equilibrium system, which are now permitted to arise.
Right.
The presence. So the point is, okay. Let me put it this way. Including noise terms that further break detail balance in some instances is important. For example, if I
Yes.
wrote down a theory of scalar active matter,
Yes.
then including, let us say, a colored noise is one of the ways in which you can introduce activity. So there's a sort of set of generic ways in which you can include activity. All of them have to do with breaking detail balance. In some instances, adding a colored noise is important. In some instances, not only the noise, but even the deterministic part of the equations of motion changes.
Yeah.
That's really all I'm saying.
Yeah. Okay.
So I don't know. I don't think we're saying very different things.
No,
in the
it's
particular
fine.
problems I showed you. Yeah.
Sure. Thank you.
Thanks.
Okay, I see that Efrat has a question.
Yeah, hi Sriram. Nice to see you.
Hi, sir.
From a distance.
Yes.
So I'm coming from the area that mostly looks at equilibrium physics. Can you say what kind of universal features you can get in such systems? Like, I mean, for
Sure,
example,
okay.
talking about these transitions, are there any universal scaling laws?
Sure. So, okay.
Yeah.
So, I mean, just to take one example, I mentioned the Berezinski-Koslitz-Thouless theory of the active nematic. As far as we can tell, at the level of analysis that we have shown in this particular case, that particular transition has the same properties as far as universal things go, meaning that you get a defect on binding. I don't know if you get, in the simple perturbative theory, there is something resembling a universal jump in the stiffness, but I'm not sure how robust that is. So I'm saying that, I guess the point is this: in some instances, introducing activity only moves you around in a phase diagram which is otherwise like the equilibrium phase diagram. In some other systems, you introduce terms which were ruled out by equilibrium physics, and therefore the symmetry changes. For example, equilibrium XY model has quasi-long-range order in 2 dimensions. An active XY model has true long-range order in 2 dimensions because the stiffness gets normalized in singular ways, which John Toner has shown. So I think the point is, in some instances, you change universality class. In some instances, the perturbation from a critical phenomena sense would be viewed as irrelevant because it merely moves you around in an existing phase diagram. Instances of both exist. In some other instances, what happens is a phase that was permitted at thermal equilibrium turns out not to survive even a small introduction of activity. For instance, as I said, the aligned phase in a Stokesian fluid, which actually aligned liquid crystalline Stokesian fluid is perfectly well behaved at thermal equilibrium. It dissolves into the complete unstable mess. So 3 kinds of things can happen. Moving around in an equilibrium, otherwise equilibrium phase diagram, changes in properties of some transitions in terms of exponents, changes in coarsening properties of some domain growth problems, and complete destruction of phases that were permitted in equilibrium, and existence of phases that were not permitted in equilibrium. All of these are possibilities. So I only showed sort of minimal examples of 1 or 2 of these in the talk. I hope that was useful to
thank you.
answer.
I think we should have time maybe for one more question. Anybody? So maybe okay.
If I can take that opportunity. Thanks again for the talk, Sriram. I have a small, I guess, question of dimension. It seems both from your talk and from the literature that there is very little about 3-dimensional active matter. You sort of started touching it with the smectic and cholesteric, although there it's not really TD. There's a direction. Reynolds in the work.
One thing is that the flocking transition that I showed you in the sort of the escape from the instability of the active flock. The bulk of our studies and our analysis is 3-dimensional there, and 3-dimensionality is actually important. You get the effect in 2 dimensions also, but 3D is actually the interesting case there. Also, now there are experiments by Zvonimir Dogic and group and some other groups on looking at active nematics in 3 dimensions. So part of the reason for the focus on 2 dimensions had been that you need to produce a system which is globally supplied with energy everywhere. That's much easier to do in 2 dimensions, either by having a surface that you shake or by having a film which is in contact with bulk nutrient. But there are now pretty good experimental systems for the 3-dimensional case also. So more results will emerge in 3 dimensions. It's happening to some degree, for instance, in our fluid flock.
Thank you.
Okay. I think if someone wants to stay for additional question, maybe Sriram can address them. But otherwise, I think we should thank again Sriram for an excellent talk. And we'll see you all in a couple of weeks for the last IPC talk. Okay, thank you very much.
Thanks very much. Thank you, Sneer and everybody. So I can log out?
Yeah, if you want, yeah. Thanks again for the talk. I'm not from the field, so it was hard for me to appreciate it, but it seems like pretty complicated stuff. Yeah, it's.
Oh dear.
Yeah, I'm coming from the equilibrium aspects, so once you add another dimensionality, it seems like it's a complete mess. But you managed to find some reasoning to it, so it's really cool. Thanks.
Thank you.
Okay, so if I disconnect this, so everyone would get logged out. So if someone wants to say, okay, so I'll just end this session. Okay, thank you.
All right, bye.
Thank you.